Welcome to a Key Stage 4 GCSE lesson on the motor effect, calculating force. So our key terms are force, magnetic flux density, current, length, and Fleming's left-hand rule. Before you start, state what is meant by a uniform magnetic field and draw the magnetic field around a current carrying wire. And finally consider, since the current carrying wire produces a magnetic field, what will happen if it is placed in an external magnetic field? Pause if you need time to complete those. And now we'll move on. So here are our key terms. Force, which is a vector quantity that can affect the speed, direction, or shape of an object. Magnetic flux density, which is the strength of a magnetic field. Current, which is the rate of flow of charge. Length, which is the distance between two opposite ends of an object. And finally, Fleming's left-hand rule, which is a method to show the direction of the force applied to a current carrying wire that's inside a magnetic field. We'll be using an equation in this lesson to calculate the force on a current carrying wire. So first we need to know what the symbols are and what the units of these different quantities are. So force is written with a capital F and its units are newtons. Magnetic flux density is written with a capital B and the units are teslas. Current is a capital I and the units are amps, and length is a lowercase l and that is measured in meters. So here is our equation for the force on a current carrying wire. We have F, the force, is equal to BIL, that is magnetic flux density, times by current, times by the length of the wire that is in the magnetic field. So the force on a current carrying wire is directly proportional to the magnetic flux density, current, and length of the wire. To work out the direction of the force on the current carrying wire, we're going to use Fleming's left-hand rule. You take your left hand and you stick your thumb up, pointing upwards, your index finger pointing forwards, and your middle finger pointing to the right. They should all be at 90 degrees from each other. Now you can remember this by doing FBI, where the thumb represents F, your index finger represents B, the magnetic field, and the direction of the current I is represented by your middle finger. You can also remember it by the mnemonic first finger field, second finger current, and the motion. So if we're given the direction of a magnetic field, that's the direction we point our index finger. We then attempt to point our middle finger in the direction of the current, and when you've done that correctly, your thumb will be pointing in the direction of the force that's acting on that wire. Now let's look at how we calculate. So if we're calculating force using the equation mentioned previously, we have 0.15 meters of wire within a uniform magnetic field of magnetic flux density 0.0020 teslas. Calculate the force on the wire when it has a current of 0.5 amps. So our first step is to write down what we know. We know that B is 0.002 teslas. We know that I is 0.5 amps. We know that L is 0.15 meters. And so the second step is to write down the equation that links these together. F equals BIL. Then, for step 3, we substitute in the numbers. So instead of B, we write 0.002. Instead of I, we write 0.5, and instead of L, we write 0.15. And then finally, in step 4, we write down our answer with correct units. The answer in this case is 0.00015 newtons. Next question. 20 centimeters of wire is within a uniform magnetic field of magnetic flux density 0.0045 Teslas. Calculate the force on the wire when it has a current of 2 amps. So our first step is to write down what we know. Now notice that we've had to convert centimeters to meters because we need to be using the SI units. That's the standard scientific units. So B is 0.0045, I is 2, and L is 0.2. Our next step is to write down the equation. Step 3 is to substitute in the numbers, and step 4 is to write the answer. Copy down steps 1 to 3 and complete step 4 yourselves. Next, we have 50 centimeters of a wire is within a uniform magnetic field of magnetic flux density 12 milliteslas. Calculate the force on the wire when it has a current of 0.5 amps. In this case, we've been given 50 centimeters and 12 milliteslas, and so we must convert these to scientific units, which are 0.012 teslas, 0.5 amps, and 0.5 meters. Step 2, write down the equation, and step 3 and 4 are to complete yourselves. Now we have 25 centimeters of wire within a uniform magnetic field of magnetic flux density 6 milliteslas. Calculate the force on the wire when it has a current of 0.9 amps. Step 1, write down what you know in scientific units. Step 2, write down your equation. Step 3, substitute in the numbers. And step 4, write your answer with correct units. Copy down step 1 and complete steps 2 to 4. Finally, for calculating force, 35 centimeters of a wire is within a uniform magnetic field of magnetic flux density 9.8 milliteslas. Calculate the force on the wire when it has a current of 3 amps. Complete all 4 steps yourselves. Now let's see what happens when we need to calculate magnetic flux density. So 0.2 meters of a wire carries a current of 0.8 amps through a uniform magnetic field. Given a force of 0.02 newtons on the wire, calculate the magnetic flux density of the field. Step 1 is to write down what we know. So force is 0.02, current is 0.8, and length is 0.2. We then write down the equation that links these together. And then step 3 is to substitute in the numbers. Now this time we don't have B on its own, and we want to make B, the magnetic flux density, the subject of the formula. So since it's B times by 0.8 and times by 0.2, we're going to divide by 0.8 and 0.2 using the rule of inverse operations from maths. This gives us that B is equal to 0.02 divided by 0.8 times 0.2. And this gives us an answer of 0.125 teslas. Copy this down and prepare for the next question. "30 centimeters of a wire carries a current of 25 amps through a uniform magnetic field. Given a force of 0.04 newtons on the wire, calculate the magnetic flux density of the field." Step 1, write down what you know. This time we must convert from centimeters to meters. Step 2, write your equation. Step 3, substitute in the numbers. Step 4, rearrange to make B the subject of the formula. And finally, step 5, write down the answer with correct units. Copy down steps 1 to 4 and complete step 5 yourselves. "55 centimeters of a wire carries a current of 12 amps through a uniform magnetic field. Given a force of 0.08 newtons on the wire, calculate the magnetic flux density of the field." So step 1, write down what you know. Step 2, write down the equation. Step 3, substitute in the numbers. And then complete steps 4 and 5 yourselves. "90 centimeters of wire carries a current of 4.5 amps through a uniform magnetic field. Given a force of 0.108 newtons on the wire, calculate the magnetic flux density of the field." Step 1, write down what you know in correct scientific units. Step 2, write the equation. And complete steps 3, 4 and 5 yourselves. "120 centimeters of a wire carries a current of 6 amps through a uniform magnetic field. Given a force of 0.05 newtons on the wire, calculate the magnetic flux density of the field." Step 1, write down what you know. Then complete steps 2 through 5 yourselves. Finally, our last calculation. 45 centimeters of a wire carries a current of 3.6 amps through a uniform magnetic field. Given a force of 2.16 newtons on the wire, calculate the magnetic flux density of the field. Complete all steps yourselves.